Okay, so we talked about neutralization reactions, but now we're going to talk about them in a bit more detail. So we're going to be focusing on pH, acids, and bases in a little bit more detail. Again, this is continuing on with section 2.4. So neutralization reactions when an acid reacts with a base. Many familiar compounds are acids and bases, so you've seen lots of these in your everyday life. Classification as acids or bases is based on chemical composition. Acids and bases are very dangerous. Both can be very corrosive. So it's not just acids that are corrosive, bases are as well. So never try to identify an acid or base by taste or touch. Even though some of the identifying factors are kind of by touch, we do not want to touch acids or bases. Okay, so symbol for this, for corrosive, danger corrosive, just images that show different effects of corrosive as well as the Wemyss symbols. Okay, so here are some examples of the pH scale, which goes from 1 to 14, 14 being the basic end, 1 being the acidic end. And some common examples like stomach acid, tomato juice on the acidic end, and then your blood, hand soap, cleaning, bleach, those are all on the basic end of the spectrum. So the strengths of acids and bases is measured on a pH scale. A pH below 7 is considered acidic, a pH above 7 is considered basic, a pH of 7 is considered neutral. So here is just a really nice color-coded example. So from 0 to 6, acidic, 7 is neutral, 8 to 14 is considered basic. Each decrease of 1 on a pH scale indicates 10 times more acidic. So for example, a pH of 4 is 10 times more acidic than a pH of 5. A pH of 3 is 1,000 times more acidic than a pH of 6. So you should know how much more acidic something is based on this 10 times rule. Essentially, you're adding a 0 every time you're going up the pH scale. pH indicators. The pH of an acid and base cannot be determined by sight. Acids and bases tend to be clear, so you're just going to look at something and be like, oh, it's a clear liquid. It looks almost identical to water. So we use things called indicators, which change color to help us determine the pH of something. So instead, pH is measured by other chemicals called indicators or by a pH meter that measures the electrical conductivity of the solution. So basically, it's measuring the amount of either H plus ions, so hydrogen ions in the solution, versus the hydroxide ions, the OH, in the solution. So here is some examples of various indicators and the colors that they change at what particular pH. pH indicators change color based on the solution they are placed in. Litmus is the most common indicator and is used on or in the form of litmus paper. So there it is off to the side. You can see that it's got a blue-purple color in the presence of a base and goes quite red in the presence of an acid. So there are two colors of litmus paper. So blue is your basic and red is your acidic. So depending on what you're testing, so it turns blue above a pH of 7 and turns red below a pH of 7. So here you can see it was dipped into a solution. The dry part is blue, meaning it's being used to test for an acid. So it's kind of opposite. So when it was dipped in the solution, it turned red, meaning that there is a pH below 7. Universal indicator, the pH color chart here, just a different type of indicator. So universal indicator contains many indicators that turn different colors in different pH values. It can be a liquid or it can be paper strips like litmus. So here you can see a spectrum of colors from acidic to basic. So based on the color, you can determine what the pH is. So for example, the middle beaker at the bottom, pretty close to a pH of 7, next to it, pH of 6, going farther left, pH of 5, 4, so on. A pH meter uses electrical probes to measure how solutions conduct electricity. Again, it's looking at those ions, so H plus hydrogen ions or OH minus ions, which dissociate when an acid or base is added to a water, meaning they separate. Here's an image of a pH meter. Indicators change color at different pH values. So different indicators are used to identify different pH values. So we have a chart that will help you with this. Bromothymol blue, for example, is useful between a range of pH 6 and 7.6. So that's shown here. You can see that the useful range is where you can see the color change. Below 5, it's going to all look yellow, and above 8, it's going to all look blue. Phenolphthalein is used for pHs above 8.2 up to 10. After 10, it's just magenta, so you can't actually differentiate. You can see the gradual color change in the range of 8.2 to 10. If it's below 8.2, it's going to appear colorless and clear. So indicators have actually been around for a really long time, and there are many natural sources. So beets can be used as an indicator. Red cabbage juice can also be used as an indicator. And litmus itself is actually from what is called a lichen, which is a symbiotic relationship you'll sometimes see in forests. So litmus is pulled from the lichen, which is used to make litmus paper. Here we have a list in the table form as well as a visual form of the various indicators and their useful range for color change. So these tables will be provided to you so you can use them on a test or quiz. But essentially you're always wanting to look within the range where it changes color, but we can use multiple indicators to determine a pH of a solution. So a few practice problems for you to try before moving on. This isn't the end of the video, so just pause here, work through these, and then we can continue on with the lesson. Here is a chart, which is an example from a chart that you will be given. So this shows us some common acids and bases and what color the indicator would be for that solution. So for example, if we focus on a banana, which has a pH of 5, if you go all the way through here, so if you've gone through all of these, you can kind of see what color they'll appear if you were to kind of mix them in a solution and test for the pH. So a banana is acidic, which has a pH of 5. So if we use methyl red, for example, the color would be slightly orange, leaning to the red end of the spectrum. Methyl orange, it would appear yellow. Bromothymol blue, it would be yellow. So you can't really get an exact pH with bromothymol blue, but you can kind of judge the pH based on methyl red because that's where you are seeing the color change. An egg, for example, has a pH of 8. So if we're looking here, you'd kind of want to compare a few different things, but it's going to be yellow and methyl orange, yellow and methyl red. It's going to be blue in bromothymol blue, blue in litmus. Phenolphthalein, it will be colorless. There might be the slightest bit of pink, depending on if it leans more above 8. And indigo carmine, it will also be blue. So complete the following tables. So this should be in your notes, but if we look back at our previous table, lemons have a pH value of 2, which makes it an acid because it's below 7. In methyl orange, it will appear red. In bromothymol blue, it will be yellow. And in litmus, it will appear red. Tomato has a pH of, actually, let's do something that's basic. So we'll do an egg again. So an egg has a pH of 8. It is considered a base. In methyl red, it's going to be yellow. And be careful with the methyl red versus methyl orange because they are different. In phenolphthalein, it is going to appear colorless / slightly pink. Depends on if it leans a bit more basic. And then indigo carmine, it is going to be blue. So pause here and make sure you finish the rest of these before moving on. I will post the answers for these. Again, a different version of the question. So this time you're given the pH indicator and the pH. You're determining if it's an acid or a base and what color the paper will be, or the indicator. So black coffee, for example, is slightly acidic. If you use blue litmus paper, it will turn red because it's in the presence of an acid. Or sorry, if you use red, it would just stay red because it's already an acid. Okay, so let's look at acids in a little bit more detail. So if you know a compound's chemical formula, you may be able to identify whether or not it's an acid. So if it has an H+, usually at the front, it is an acid. Acids often behave like acids only when dissolved in water. So if it's a gas or a solid, it won't act like an acid. Therefore, acids are often written with the symbol AQ, which stands for aqueous. And remember, aqueous again means it's being dissolved in water. So for our example, hydrogen chloride, I guess, before it enters the water, it's dissolved, so it becomes aqueous, which is what allows it to kind of give off or dissociate, lose its hydrogen ion. It's not actually lost, it's in the solution, but it's just removed from the chloride, and this is what makes it an acid. So the H+ ion that the acid gives off when dissolved is what makes an acid an acid. So sulfuric acid is also used in batteries. That's another example at the bottom there. So most acids typically start with a hydrogen. So for example, hydrochloric acid, HCl, HF, HBr. They are only an acid when they are dissolved in water. And this is because they are able to, that H+ is allowed to come off the other element. There are some acids which are more carbon-based. In these cases, carbon will be written first. So we've got HCl, which when aqueous is hydrochloric acid, HNO3 is nitric acid, CH3COOH is your carbon acid. This is acetic acid as the common name. So you likely know this as vinegar. It is an organic acid. And the hydrogen, you'll notice, is written at the end instead of at the beginning. So important to keep this in mind, that it usually starts with hydrogen in front of the formula, but it may also appear at the end for our acids. So feel free to pause here. I believe this table is also in your notes, but these are just some other acids that you will learn how to name, and their common names which may also appear. Okay, so we're going to move on to classifying acids. So there are two types of acids, binary acids and oxy acids. Binary acids usually contain two elements or only contain two elements. So for example, HF is hydrofluoric acid, and oxy acids contain oxygen as part of a polyatomic ion. For example, H2SO4 is, it contains a sulfate ion which has an oxygen. So it's because the polyatomic contains an oxygen that it is considered an oxy acid. So the namings for these are a little bit different. So to begin, we're going to start with naming binary acids. The rule for this is hydrogen plus something that ends in IDE becomes hydro, and then drop the IDE, acid. So hydrogen plus a nonmetal, we drop the gen from hydrogen, and instead of changing the ending to IDE, it becomes IC, and then we add the word acid. So for our hydrofluoric acid example, HF, previous naming would tell us that this is hydrogen fluoride. When we dissolve this in water, it becomes an acid with the name hydrofluoric acid. So we dropped the gen from hydrogen, and we dropped the IDE ending from fluoride, changing it to IC, so fluoric, and we add the word acid, so hydrofluoric acid. There's a table here with some other common binary acids. So HCl, hydrogen chloride, becomes hydrochloric acid. HBr, hydrogen bromide, hydrobromic acid. HI, hydrogen iodide, hydroiodic acid when dissolved in water. And it also gives you some examples of its uses. Try the name and formulas of these acids below. I'm going to give you the first one. So HCl, based on traditional naming, is hydrogen chloride. So we are going to drop the gen, change the IDE. So we've got hydrochloric, and then we add the word acid. So pause here, try the remaining ones. The answers will be given to you on the next slide. So we did hydrochloric acid together. HI is hydrogen iodide, which we drop the gen, change the IDE, becomes IC, hydroiodic acid. HCN, hydrogen cyanide, so this is a polyatomic. So drop the gen, change the ending of cyanide, hydrocyanic acid. So note that there are 3 different elements in this one because CN is a polyatomic, but because none of them are oxygen, even though it's a polyatomic, it follows the binary acid rules. It is not an oxy acid. And then hydrobromic acid, you're given the acid name, you're making the formula, so it is HBr. Okay, so make sure you've got these corrected. If you made a mistake and you don't understand, please reach out to me and ask. So here again are the overall rules for naming a binary acid. So hydrogen plus something IDE, we drop the gen, change the ending to ic, add acid. And again, that table summarizes the binary acids and all of its use. Okay, naming oxy acids. So they have a polyatomic ion and they end differently. So what does that look like? So you've probably noticed that some of the polyatomics have different endings. For example, NO3 is nitrate, NO2 is nitrite. These endings will determine how we name our oxy acids. So if a polyatomic ends in 8, we replace it with IC, IC, and get rid of the hydrogen entirely from the name. So H2CO3 is hydrogen carbonate. Drop the hydrogen entirely, change the ending to ic, so it becomes carbonic acid. So when we take hydrogen carbonate and dissolve it in water, it becomes carbonic acid. Second example, if a polyatomic ends in ite, ITE, we again remove the hydrogen and end it with OS, OUS acid. Okay, so for the second oxy acid, you've got hydrogen plus some polyatomic that ends in ITE. For this type of oxy acid, we drop the hydrogen just like before and replace the ITE ending with OUS. So for example, H2SO3, SO3 is sulfite, so hydrogen sulfite before it's dissolved in water becomes, we drop the hydrogen, change the ITE to OUS, and add the word acid. So it becomes sulfurous acid. The bottom right table shows you some other common oxy acids, as well as some examples. So important to know, we drop the hydrogen, change 8 to ic, so perchloric acid, hydrogen chlorate, drop the hydrogen, change the 8, it becomes chloric acid. Same thing, ite to os, ite to os. So it is important that you know these naming rules. To help you remember, there are some words you can use. These aren't a perfect fit, but they're fairly close. If you can come up with your own, feel free. Usually that will probably result in you remembering them better. But for these words, for the ite to OUS naming change, so for your polyatomics that end in ITE, like the hydrogen sulfite, we use the word righteous to remember this. So ite sounds like right, and then it ends in the letters OUS, so righteous. The second one, so for the 8 oxy acids, ATE, not the number 8, we use the word pathetic. Now this one, as I said, is more of a stretch, but path E, basically, the first part of the word, kind of looks like 8. Again, a little bit of a stretch because there's an H in there. So this part here, but it does end in IC. So that is the ick part. So pathetic or righteous to remember this. Okay, and some practice for you to try. There's also a little bit more at the bottom of your page. So pause here. The naming trick thing is at the bottom there to help you. But yeah, pause and then you can check your answers on the next slide. Okay, so going through the answers here, the first one is broken down a bit more, but SO4 is sulfate, so it's an ick acid. So we drop the hydrogen, change the ATE ending to ick, and it becomes sulfuric acid. HNO3, hydrogen nitrate becomes nitric acid. HNO2 is nitrite, so hydrogen nitrite to nitrous acid. And then these ones are going to the formula. So phosphoric acid tells us we need to go back to 8, which is PO4 for this one. So H3PO4. And chlorus tells us we have an ITE ending. So we're dealing with chlorite, so HClO. Okay, and then some practice questions as well. I think these are the ones at the bottom of your page in your notes. Important to know for number 2A, your stomach acid is referred to as hydrochloric acid. So just so you are aware. And then work through these before moving on to the base section. Okay, so moving on to bases. If you know a compound's chemical formula, you may be able to identify it as a base. Bases often behave like bases only when dissolved in water, so same as acids. So needs to be dissolved in water, otherwise it is not an acid or a base. Therefore, bases are often written with the symbol AQ, aqueous, which again means it's dissolved in water. The chemical formula of a base usually ends with hydroxide, which is OH. So in the bottom image there, you can see that when you drop sodium hydroxide into water, it dissociates into or splits up into sodium ions and hydroxide ions. It is the hydroxide ion that splits off that makes this a base. Bases are commonly also household cleaning ingredients. So bases can be gentle or very caustic. They can also be super corrosive. So not just acids are corrosive. So examples of common bases, NaOH is sodium hydroxide. You've seen this in your labs over the years, not just this year. Magnesium hydroxide, calcium hydroxide, and ammonium hydroxide. Okay, so the table at the bottom, and I'll put these up for you. There you go. So those are all the ones that I just listed off. The table provides some more information. A lot of these, as I said, are used in cleaners. So one of the examples is an antacid, which is right here. Magnesium hydroxide is known as milk of magnesia. So it's something that we ingest to help with increased level of stomach acid, which can cause heartburns. And so that basically helps to neutralize the extra acid. Bases, unlike acids, are really nice and easy to name, so that's good. There's no real changes with the ending. You just have to know that it ends in hydroxide, so sodium hydroxide, etc. Okay, so same as before, pause here, do a quick check of your understanding, and then you can move on. Okay, production of ions. So kind of mentioned pH meters earlier on, as they can be used to detect the pH of an acid or base. The pH meter detects electrical conductivity. Acids and bases are both compounds that release ions when dissolved in water. So acids release hydrogen ions, which are H+, and bases release hydroxide ions, which is OH minus. So here's just an overall table. So to the right from neutral, you're increasing acidity, which means we are increasing the concentration of hydrogen ions. So these little square brackets you see here indicates concentration. So it's basically a short form so that we don't have to write out the concentration of hydrogen ions. As you move to the right from neutral, it becomes more basic, so basicity increases. This is an increase in hydroxide ions, so OH. And then it's important to know that if you combine hydrogen ions with hydroxide ions, it forms water, which is where that neutralization occurs. The pH of a solution refers to the concentration of ions it has. So again, those little square brackets symbolize concentration. So square brackets are used to signify concentration. So for example, concentration of hydrogen ions and concentration of hydroxide ions. If you have high concentration of hydrogen ions, you're going to have a very low pH, and this is going to be very acidic. If you have a high concentration of hydroxide ions, you're going to have a high pH, meaning it's very basic, or the solution is very basic, because remember, we're dealing with solutions with acids and bases. So again, here's just that table again, which shows that as you lower the pH, you're getting an increase in hydrogen ions. As you increase the pH, you're getting an increase in hydroxide ions. A solution cannot have both high hydrogen ion concentration and high hydroxide ion concentration. They cancel each other out and form water. This process is called neutralization. So we've got a hydrogen ion combining with a hydroxide ion, it will form water. So if you count out, it's got two H's, one O, that is the formula for water. Here are a few properties of acids and bases. It's important that you are able to differentiate between acids and bases based on these properties. So you should know these. Acids are generally more sour, so think lemons. They get their flavor from citric acid. Bases are generally bitter. Think like tonic water. Guanine is the base in tonic water that makes it taste bitter. Acids typically burn your skin. Bases can burn your skin, but generally feel more slippery. This is where soap gets its slippery feel. Now it says bases are slippery, but that doesn't mean in an acid or in a lab that you should go kind of feeling the base. That will cause burns, so do not do this. It's just saying that a low level base like soap has that slippery feel. Many different indicators for acids and bases. You use indicator charts to figure out which one will be the most useful and applicable. Acids react with metals, bases do not. Both are electrically conductive because they give off ions. Acids have a pH below 7, bases are above 7. Acids produce hydrogen ions, bases produce hydroxide ions. So there are a few questions in your notes to determine if different substances are acids or bases. So take a few minutes to work through that. And then this is basically it for the section on acids, bases, and pH. Okay. And there is just a point there that the hydrochloric acid plus magnesium metal produces hydrogen gas. This was the hydrogen pop test that you might have done in earlier years, usually Science 9. It is repeated again in Science 10 though. Yeah, so that's the end of this section. Follow the schedule and move on to whatever has been assigned to you.